Look up on a clear night and you'll see stars scattered across the darkness, thousands of them, each a sun in its own right. But here's something that should make you pause. Every single one of those stars belongs to our galaxy. The Milky Way isn't just our home, it's our prison. Beyond its boundaries lies a void so vast, so fundamentally insurmountable, that humanity will never escape it. Not with rockets, not with warp drives, not even if we had 1,000,000 years to try. The universe has locked us in, and the key isn't hidden, it's been destroyed by the expansion of space itself. While we dream of exploring distant galaxies, physics has already written the final chapter of that story. We're trapped in the Milky Way forever, and the reasons why reveal some of the most profound and unsettling truths about the cosmos, the cosmic speed limit that seals our fate. Einstein's theory of special relativity established the speed of light as the ultimate speed limit of the universe, 299,792,458 meters per second, or about 186,282 miles per second. This isn't just a suggestion or a barrier waiting to be broken with better technology. It's a fundamental property woven into the fabric of space-time itself. Nothing with mass can reach or exceed this speed, regardless of how much energy is applied. This cosmic speed limit creates an immediate and insurmountable problem for intergalactic travel. The Andromeda galaxy, our nearest large galactic neighbour, sits approximately 2.5 million light-years away. Even if we could build a spacecraft capable of travelling at the speed of light, something that's physically impossible for any object with mass, it would still take 5 million years to reach Andromeda. That's not a journey measured in human lifetimes, or even in the span of human civilization. It's longer than Homo sapiens has existed as a species. Andromeda is close by galactic standards. The observable universe extends roughly 46.5 billion light-years in every direction from Earth. But the vast majority of galaxies lie billions of light-years away. The light we see from many distant galaxies was emitted when the universe was young, when Earth didn't exist, when the Milky Way itself was still forming. Reaching those galaxies would require travel times measured not in millions but in billions of years longer than the age of the Sun, longer than complex life has existed on Earth. Even if we assume some future breakthrough allows travel at 99% the speed of light, relativistic effects would cause time to pass differently for travellers compared to those who remain behind. From the perspective of Earth, a journey to Andromeda and back would take over 5 million years. Civilizations would rise and fall. Species would evolve and go extinct. The Earth itself might become unrecognizable or uninhabitable. The travellers, experiencing time dilation, might age only decades during the journey, but they would return to a world that no longer exists in any meaningful sense. This isn't pessimism, it's mathematics. The equations of special relativity are as well tested and reliable as any in physics. They describe how the universe actually behaves, not how we wish it would. The speed of light isn't a technological barrier waiting to be overcome. It's a fundamental limit built into the structure of reality itself. And it means that intergalactic distances, measured in millions and billions of light years, translate into travel times so enormous that they dwarf human comprehension. Some have proposed theoretical workarounds, wormholes that connect distant points in space, or Alcubierre drives that compress space in front of a ship and expand it behind. But these concepts require exotic forms of matter with negative energy density, something that has never been observed and may not exist. Even if such matter could be found or created, the energy requirements would be staggering, potentially requiring more energy than exists in multiple stars. These aren't engineering challenges, they're barriers that may be fundamentally insurmountable. The cosmic speed limit doesn't just make intergalactic travel difficult, it makes it effectively impossible for any civilization bound by the laws of physics as we understand them. We are separated from other galaxies, not by distance alone, but by a combination of distance and physical law that creates an unbridgeable gulf. The universe has placed us in the Milky Way and thrown away the key. The expanding universe tears apart our cosmic neighbourhood. The speed of light isn't the only thing keeping us trapped in the Milky Way. The universe itself is expanding, and that expansion fundamentally changes what it means to travel between galaxies. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, with their recessional velocities increasing with distance. This wasn't because galaxies were moving through space, it was because space itself was expanding, carrying galaxies along with it. This expansion is described by the Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec. What this means is that for every 3.26 million light-years of distance, the expansion of space causes galaxies to recede from each other at an additional 70 kilometers per second. For nearby galaxies, this effect is negligible. Gravity easily overcomes the expansion and keeps galaxies bound together in clusters and groups. But over vast distances, the expansion dominates. At a distance of about 4,200 megaparsecs, roughly 13.7 billion light-years, galaxies are receding from us at the speed of light. Beyond this distance, known as the Hubble radius, galaxies recede faster than light itself. This doesn't violate special relativity, because the galaxies aren't moving through space faster than light. Space itself is expanding faster than light can cross it. The result is the same. Light from galaxies beyond the Hubble radius will never reach us, and we could never reach them even if we could travel at the speed of light. But the situation is worse than this simple calculation suggests. The expansion of the universe isn't constant, it's accelerating. In 1998, observations of distant supernovae revealed that the universe's expansion rate is increasing over time, driven by a mysterious component called dark energy. This discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of the universe's fate. Dark energy makes up approximately 68% of the total energy density of the universe. Unlike matter and radiation, which become more dilute as space expands, dark energy maintains a constant density. As the universe grows larger, the total amount of dark energy increases, causing the expansion to accelerate ever faster. This acceleration has profound implications for the future of cosmic travel. Currently, galaxies within the local group, including the Milky Way, Andromeda, and about 54 smaller galaxies, are gravitationally bound to each other. Their mutual gravitational attraction is strong enough to overcome the expansion of space, keeping them together as a coherent structure. But beyond the local group, the expansion takes over. Galaxies in the Virgo cluster, about 54 million light-years away, are receding from us at roughly 1,200 kilometers per second. More distant structures recede even faster. As dark energy continues to drive accelerating expansion, the observable universe will shrink in a practical sense. Galaxies currently visible will be carried away faster and faster, their light redshifted into longer and longer wavelengths until they fade from view entirely. In approximately 150 billion years, galaxies beyond the local group will have receded beyond our cosmic horizon, becoming forever unreachable and unobservable. The local group will become isolated, an island in an increasingly empty cosmos. This means that even if we could somehow overcome the speed of light barrier, even if we develop technology capable of traveling at relativistic speeds, the expanding universe would work against us. A galaxy currently 10 million light-years away isn't a static target waiting for us to reach it. By the time we travelled even a fraction of that distance, the expansion of space would have carried it significantly farther away. We would be like runners on a treadmill, expending enormous energy to move forward while the destination retreats faster than we can chase it. The energy problem makes interstellar travel nearly impossible. Even within the Milky Way, the energy requirements for meaningful space travel present obstacles so severe they border on insurmountable. To understand why, we need to examine what it actually takes to accelerate a spacecraft to velocities high enough to make interstellar distances traversable within human-relevant timeframes. The kinetic energy of an object increases with the square of its velocity. At everyday speeds, this is manageable. But as velocities approach relativistic speeds, a significant fraction of the speed of light, the energy requirements become astronomical. To accelerate a single kilogram of mass to 90%, the speed of light requires approximately 1.8 times 10, 17 joules of energy. That's roughly equivalent to the total energy output of a large nuclear power plant running continuously for 6 years, all to accelerate just 1 kilogram. A spacecraft capable of carrying even a small crew would need to mass at least several thousand kilograms when accounting for life support, radiation shielding, propulsion systems, and supplies. Accelerating a 10,000 kilogram spacecraft to 90% light speed would require about 1.8 times 10, 21 joules more energy than the entire United States cons. Look up on a clear night and you'll see stars scattered across the darkness, thousands of them, each a sun in its own right. But here's something that should make you pause. Every single one of those stars belongs to our galaxy. The Milky Way isn't just our home, it's our prison. Beyond its boundaries lies a void so vast, so fundamentally insurmountable, that humanity will never escape it. Not with rockets, not with warp drives, not even if we had 1,000,000 years to try. The universe has locked us in, and the key isn't hidden, it's been destroyed by the expansion of space itself. While we dream of exploring distant galaxies, physics has already written the final chapter of that story. We're trapped in the Milky Way forever, and the reasons why reveal some of the most profound and unsettling truths about the cosmos. The cosmic speed limit that seals our fate. Einstein's theory of special relativity established the speed of light as the ultimate speed limit of the universe, 299,792,458 meters per second, or about 186,282 miles per second. This isn't just a suggestion or a barrier waiting to be broken with better technology. It's a fundamental property woven into the fabric of space-time itself. Nothing with mass can reach or exceed this speed, regardless of how much energy is applied. This cosmic speed limit creates an immediate and insurmountable problem for intergalactic travel. The Andromeda galaxy, our nearest large galactic neighbour, sits approximately 2.5 million light-years away. Even if we could build a spacecraft capable of travelling at the speed of light, something that's physically impossible for any object with mass, it would still take 2.5 million years to reach Andromeda. That's not a journey measured in human lifetimes or even in the span of human civilization. It's longer than Homo sapiens has existed as a species. Andromeda is close by galactic standards. The observable universe extends roughly 46.5 billion light-years in every direction from Earth. But the vast majority of galaxies lie billions of light-years away. The light we see from many distant galaxies was emitted when the universe was young, when Earth didn't exist, when the Milky Way itself was still forming. Reaching those galaxies would require travel times measured not in millions, but in billions of years, longer than the age of the Sun, longer than complex life has existed on Earth. Even if we assume some future breakthrough allows travel at 99% the speed of light, relativistic effects would cause time to pass differently for travellers compared to those who remain behind. From the perspective of Earth, a journey to Andromeda and back would take over 5 million years. Civilizations would rise and fall, species would evolve and go extinct. The Earth itself might become unrecognizable or uninhabitable. The travellers, experiencing time dilation, might age only decades during the journey, but they would return to a world that no longer exists in any meaningful sense. This isn't pessimism, it's mathematics. The equations of special relativity are as well tested and reliable as any in physics. They describe how the universe actually behaves, not how we wish it would. The speed of light isn't a technological barrier waiting to be overcome. It's a fundamental limit built into the structure of reality itself. And it means that intergalactic distances, measured in millions and billions of light-years, translate into travel times so enormous that they dwarf human comprehension. Some have proposed theoretical workarounds, wormholes that connect distant points in space, or Alcubierre drives that compress space in front of a ship and expand it behind. But these concepts require exotic forms of matter with negative energy density, something that has never been observed and may not exist. Even if such matter could be found or created, the energy requirements would be staggering, potentially requiring more energy than exists in multiple stars. These aren't engineering challenges, they're barriers that may be fundamentally insurmountable. The cosmic speed limit doesn't just make intergalactic travel difficult, it makes it effectively impossible for any civilization bound by the laws of physics as we understand them. We are separated from other galaxies not by distance alone, but by a combination of distance and physical law that creates an unbridgeable gulf. The universe has placed us in the Milky Way and thrown away the key. The expanding universe tears apart our cosmic neighbourhood. The speed of light isn't the only thing keeping us trapped in the Milky Way. The universe itself is expanding, and that expansion fundamentally changes what it means to travel between galaxies. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, with their recessional velocities increasing with distance. This wasn't because galaxies were moving through space, it was because space itself was expanding. carrying galaxies along with it. This expansion is described by the Hubble constant, currently measured at approximately 70 kilometers per second per megaparsec. What this means is that for every 3.26 million light-years of distance, the expansion of space causes galaxies to recede from each other at an additional 70 kilometers per second. For nearby galaxies, this effect is negligible. Gravity easily overcomes the expansion and keeps galaxies bound together in clusters and groups. But over vast distances, the expansion dominates. At a distance of about 4,200 megaparsecs, roughly 13.7 billion light-years galaxies are receding from us at the speed of light. The energy problem makes interstellar travel nearly impossible. Even within the Milky Way, the energy requirements for meaningful space travel present obstacles so severe they border on insurmountable. To understand why, we need to examine what it actually takes to accelerate a spacecraft to velocities high enough to make interstellar distances traversable within human-relevant timeframes. The kinetic energy of an object increases with the square of its velocity. At everyday speeds, this is manageable. But as velocities approach relativistic speeds, a significant fraction of the speed of light, the energy requirements become astronomical. To accelerate a single kilogram of mass to 90% the speed of light requires approximately 1.8 times 10, 17 joules of energy. That's roughly equivalent to the total energy output of a large nuclear power plant running continuously for 6 years, all to accelerate just 1 kilogram. A spacecraft capable of carrying even a small crew would need to mass at least several thousand kilograms when accounting for life support, radiation shielding, propulsion systems, and supplies. Accelerating a 10,000 kilogram spacecraft to 90% light speed would require about 1.8 times 10, 21 joules more energy than the entire United States consumes in a year. And that's just to accelerate the spacecraft. You'd need the same amount of energy to decelerate it at the destination, doubling the total requirement. The problem compounds when we consider what energy source could possibly provide this. Chemical rockets, the technology that sent humans to the moon, are woefully inadequate. The most energetic chemical reactions release only about 10 million joules per kilogram of fuel. To reach relativistic speeds using chemical rockets would require more fuel than exists in multiple planets. Nuclear fission offers better energy density, but even fission couldn't provide the power-to-weight ratio needed for relativistic travel without requiring absurd amounts of fuel. Nuclear fusion, the process that powers stars, offers more promise. Fusion of hydrogen into helium releases about 600 trillion joules per kilogram of fuel, far more than any chemical process. But even fusion faces limitations. The inefficiencies inherent in any real engine mean that only a fraction of the fuel's energy gets converted into kinetic energy of the spacecraft. Even with a perfectly efficient fusion drive, something that violates thermodynamics, you'd need to carry thousands of kilograms of fuel to accelerate a small spacecraft to relativistic speeds. Antimatter offers the highest possible energy density. Annihilation of matter and antimatter converts mass directly into energy according to Einstein's E=mc², releasing about 90 million trillion joules per kilogram. This is the absolute maximum energy you can extract from matter. Even with antimatter, accelerating a modest spacecraft to 90% light speed would require hundreds of kilograms of antimatter. Current antimatter production capabilities measure in nanograms per year. At current production rates, it would take billions of years to produce the antimatter needed for a single interstellar voyage. Beyond the fuel problem lies the issue of propulsion itself. Conventional rockets work by ejecting mass backward to push the spacecraft forward. To achieve high speeds, you need to eject that mass at extremely high velocities, which requires even more energy. The tyranny of the rocket equation means that for any given exhaust velocity, there's a limit to how fast you can accelerate a spacecraft before the fuel requirements become infinite. Even theoretical propulsion concepts like ion drives or photon rockets face this fundamental constraint. Some have proposed building massive lasers or microwave beamers on Earth or in orbit, using them to push lightweight spacecraft to relativistic speeds, using radiation pressure. The Breakthrough Starshot project envisions using ground-based lasers to accelerate tiny chip-sized spacecraft to 20% light speed. But scaling this approach to spacecraft large enough to carry humans faces immense challenges. The power requirements for the laser array would be enormous, potentially hundreds of gigawatts. Focusing such a beam across interstellar distances introduces further complications, as diffraction causes the beam to spread, reducing its effectiveness over distance. Radiation in deep space would kill any crew. Space isn't empty, it's filled with radiation that poses severe hazards to human health, and these hazards grow exponentially worse as you venture beyond the protective bubble of Earth's magnetic field and attempt journeys lasting decades or centuries. The radiation environment of deep space represents a fundamental barrier to human interstellar travel that no amount of engineering can fully overcome. Galactic cosmic rays, GCRs, are high-energy particles, primarily protons and atomic nuclei, that originate from supernovae and other energetic events throughout the galaxy. These particles travel at nearly the speed of light and carry tremendous energy. Unlike the charged particles in solar wind, which Earth's magnetic field deflects, GCRs possess enough energy to penetrate deep into spacecraft and human tissue. A typical GCR flux in deep space delivers approximately 0.4 to 0.6 sieverts of radiation per year, about 200 times the radiation dose a person receives on Earth from natural sources. The biological effects of this radiation are severe. When high-energy particles strike DNA molecules in human cells, they cause double-strand breaks damage to both strands of the DNA helix simultaneously. These breaks are difficult for cells to repair correctly, often leading to mutations. Exposure to GCR levels typical of deep space increases cancer risks substantially. NASA estimates that a Mars mission lasting 2 to 3 years would expose astronauts to radiation doses that increase their lifetime cancer risk by approximately 5%. An interstellar journey lasting decades would increase cancer risk close to certainty, but cancer is only part of the problem. Recent studies of astronauts who spent time on the International Space Station, where they receive far less radiation than they would in deep space, showed troubling cognitive effects. Exposure to cosmic radiation damages neurons in the brain, particularly in the hippocampus, which is crucial for memory formation and spatial navigation. Animal studies simulating deep space radiation exposure show persistent cognitive deficits, increased anxiety, and impaired decision-making effects that could prove catastrophic on a multi-decade voyage where crew members must maintain spacecraft systems and respond to emergencies. Cosmic ray exposure also damages the cardiovascular system. Studies of astronauts who flew to the Moon during the Apollo program, the only humans to leave Earth's magnetic field, show significantly elevated rates of cardiovascular disease compared to astronauts who only flew in low Earth orbit. The mechanism appears to involve radiation damage to cells lining blood vessels, promoting atherosclerosis and increasing stroke and heart attack risk. Shielding against GCRs presents enormous challenges. Unlike lower energy radiation that can be blocked with thin layers of metal or plastic, GCRs require substantial shielding mass. Aluminum, a common spacecraft material, actually makes the problem worse through a process called secondary radiation. When a high-energy cosmic ray strikes an aluminum atom, it produces a shower of secondary particles, some of which are more biologically damaging than the original particle. Materials rich in hydrogen, like water or polyethylene, provide better shielding, but the mass requirements remain prohibitive. To reduce radiation exposure to safe levels for a multi-year journey, a spacecraft would need several meters of water or polyethylene shielding surrounding all inhabited areas. For a small spacecraft, this could add hundreds of tons of mass, dramatically increasing the energy requirements for acceleration and deceleration. The shielding itself would need shielding against micrometeorite impacts, adding even more mass. The engineering challenges of building and launching such a heavily shielded craft are immense. Solar particle events, SPEs, present another hazard. These are bursts of high-energy particles ejected by the Sun during solar flares and coronal mass ejections. While less energetic than GCRs, SPEs can deliver extremely high radiation doses over short periods, potentially lethal doses within hours during major events. Spacecraft would need dedicated storm shelters, small, heavily shielded areas where crew members could take refuge during SPEs. But predicting SPEs is difficult, and some occur with little warning. Beyond radiation's direct biological effects, there's the issue of electronics. Cosmic rays can cause single-event upsets, bit flips in computer memory that corrupt data or cause malfunctions. Spacecraft systems require extensive redundancy and error correction to operate reliably in deep space. A ship traveling for decades or centuries would need systems robust enough to withstand countless cosmic ray hits without catastrophic failure. Time dilation makes interstellar journeys generational nightmares. According to special relativity, time passes more slowly for objects moving at high velocities relative to stationary observers. This effect, called time dilation, becomes significant as velocities approach the speed of light. While time dilation might seem like an advantage for interstellar travel, allowing travelers to age less during long journeys, it actually creates profound practical and philosophical problems that make human interstellar colonization nearly impossible. Consider a spacecraft traveling to Proxima Centauri, the nearest star system at 4.24 light-years away, at 90% the speed of light. For observers on Earth, the journey would take approximately 4.7 years, the distance divided by the velocity, accounting for acceleration and deceleration. But for the travelers aboard the spacecraft, time dilation would slow their clocks. Using the Lorentz factor, the crew would experience only about 2 years of elapsed time during the journey. This seems advantageous. The crew ages only 2 years, while covering 4.24 light-years. But the situation grows more complicated when communication is considered. Radio signals from Earth, traveling at the speed of light, would be severely redshifted from the spacecraft's perspective due to relativistic Doppler effects. Communications would be delayed, distorted, and increasingly difficult. By the time the spacecraft reached Proxima Centauri, 4.7 years would have passed on Earth. Any response to a message sent from the spacecraft would take another 4.24 years to travel back at light speed. The total communication round-trip time exceeds 9 years from Earth's perspective, nearly 5 times the subjective journey time for the crew. This temporal disconnect severs the travelers from their homeworld in a fundamental way. The Earth they left would not be the Earth that receives news of their arrival. Friends, family members, and colleagues would have aged nearly a decade while the travelers aged only 2 years. Return to Earth would compound the effect. A round trip at the same velocity would result in travelers who had aged only 4 years returning to an Earth where 4 years had passed. They would be younger than siblings who were once younger, would return to find their children grown, their parents elderly or deceased. These effects become far more severe for journeys to more distant destinations. A trip to a star 1,000 light-years away, at 99.99%. The speed of light would take approximately 1,000 years from Earth's perspective, but only about 14 years for the travelers due to extreme time dilation. The travelers would return to an Earth 2,000 years in the future, a planet where their entire civilization has been replaced by something utterly different, where languages have evolved beyond recognition, where technology has advanced in unpredictable ways, where the political and social structures they knew have vanished. This creates an unsolvable problem for establishing an interstellar civilization. If travel times between stars are measured in decades or centuries from Earth's perspective, but years or decades from travelers' perspectives, maintaining any kind of coherent multi-star society becomes impossible. Each colony would evolve independently, separated not just by space but by relativistic time effects that make synchronization of calendars, governance, trade, or culture meaningless. The generational ship concept proposed as a solution to the time problem by having multiple generations live and die during centuries-long journeys creates its own nightmares. A vessel carrying thousands of people on a 500-year journey would need to function as a completely self-sustaining closed ecosystem. Every atom of air, water, and food would need to be recycled with perfect efficiency for centuries. Any failure in life support, any unexpected technical problem, any social breakdown would be catastrophic, with no possibility of rescue or resupply. The cosmic void between galaxies is unimaginably empty. The space between galaxies makes the vast emptiness between stars look crowded by comparison. Intergalactic space is a void of such profound emptiness that it challenges human comprehension and creates practical obstacles to travel that extend far beyond mere distance. In interstellar space, the regions between stars within a galaxy, the average density of matter is approximately 1 atom per cubic centimetre. This is an incredibly good vacuum by terrestrial standards, far better than anything achieved in laboratories on Earth. But in intergalactic space, the density plummets to about 1 atom per cubic metre or less. To put this in perspective, if you took a volume of intergalactic space the size of Earth and collected all the atoms within it, You'd have less mass than a small asteroid. This extreme emptiness means that conventional concepts of fueling stations or resources simply don't exist between galaxies. A spacecraft travelling through intergalactic space couldn't gather hydrogen for fusion reactors using a Bussard ram scoop, a theoretical device that would scoop up interstellar hydrogen to fuel a fusion drive because there isn't enough material to scoop. The spacecraft would be on its own, carrying every atom needed for propulsion, life support, and repairs for millions of years. Navigation through intergalactic space presents challenges completely different from navigation within a galaxy. In interstellar space, nearby stars provide reference points for navigation. Their positions change measurably over decades due to proper motion, but they remain visible and useful as guideposts. In intergalactic space, there are no nearby reference points. The home galaxy and the destination galaxy would both appear as small, distant patches of light, their apparent positions barely changing over centuries. Determining position and velocity with sufficient accuracy to ensure the spacecraft reaches its destination would require extraordinary precision in navigation systems that must function flawlessly for millions of years. The cosmic microwave background, CMB, the faint afterglow of the Big Bang, fills intergalactic space with microwave radiation at a temperature of 2.7 Kelvin. While this seems negligible, a spacecraft travelling at relativistic speeds would experience extreme blue shifting of this radiation. The CMB photons would appear shifted to higher energies in the spacecraft's forward direction, potentially reaching X-ray or even gamma-ray energies. This would subject the front of the spacecraft to continuous bombardment by high-energy radiation, heating the vessel and damaging electronics and materials over time. Intergalactic space is also pervaded by the intergalactic medium, IgM, a tenuous plasma of ionized hydrogen and helium left over from the Big Bang and enriched by material ejected from galaxies. While extremely diffuse, the IgM isn't perfectly uniform. It contains slightly denser regions that might be detectable as obstacles only at close range. A spacecraft travelling at 0.9 C would cross 1 light-year in about 1.1 years ship time. If it encountered an unexpected density enhancement in the IgM, there would be essentially no time to maneuver. The collision between the spacecraft and the IgM at relativistic speeds would be catastrophic. Each hydrogen atom would strike the vessel with kinetic energy equivalent to a particle in an accelerator. Dark energy guarantees permanent galactic isolation. Dark energy, the mysterious force driving the accelerated expansion of the universe, represents perhaps the most insurmountable barrier to intergalactic travel. Unlike the other obstacles we've discussed, which are merely extremely difficult, dark energy creates a physical impossibility that no conceivable technology can overcome. Current measurements indicate that dark energy makes up approximately 68% of the total energy density of the universe. Its nature remains one of the biggest mysteries in physics. The leading explanation is that it's a property of space itself, a cosmological constant that creates a kind of intrinsic pressure causing space to expand. Regardless of its nature, its effects are well measured and undeniable. The key property of dark energy is that its density remains constant as the universe expands. Unlike matter, which becomes more dilute as space stretches, dark energy maintains the same energy per unit volume. This means that as the universe grows, the total amount of dark energy increases proportionally. With more dark energy comes stronger acceleration, creating a runaway feedback loop. Right now, galaxies within the local group, our gravitationally bound cluster of galaxies including the Milky Way, Andromeda, Triangulum, and about 50 dwarf galaxies remain gravitationally bound, despite the expansion of space. Their mutual gravitational attraction exceeds the expansion rate in this local region, keeping them together as a coherent group. But beyond the local group, dark energy dominates. The Virgo cluster, our nearest large cluster of galaxies at about 54 million light-years away, is receding from us at approximately 1,200 kilometers per second due to cosmic expansion. The Coma cluster, about 320 million light-years distant, recedes at roughly 7,000 kilometers per second. The expansion velocity increases with distance, and there's nothing we can do to reverse it. These galaxies are being carried away from us by the expansion of space itself. As dark energy continues to drive accelerating expansion, this situation will worsen. Currently, the age of the universe is about 13.8 billion years, and the acceleration has been ongoing for roughly the last 5 to 6 billion years. Over the next 100 billion years, the expansion rate will increase dramatically. Galaxies currently within reach, in principle, will accelerate beyond the cosmic event horizon, the boundary beyond which light can never reach us. Simulations of the universe's future under continued dark energy dominance paint a stark picture. In about 150 billion years, every galaxy beyond the local group will have been carried beyond our cosmic horizon. Their light, stretched to infinite wavelengths, will fade from view. From the perspective of observers in our local group, the observable universe will consist only of the merged remnant of the Milky Way and Andromeda, the galaxy we call Milkomeda, plus the few dozen dwarf galaxies gravitationally bound to us. This isn't just about what we can see, it's about what we can reach. A galaxy that has receded beyond the cosmic event horizon is not merely difficult to reach, it is physically impossible to reach. Even a spacecraft travelling at the speed of light, departing today, would never catch up to such a galaxy. The space between us and it would expand faster than the spacecraft could traverse it, like running on a treadmill that accelerates faster than you can run. The most disturbing aspect is the irreversibility of this process. Dark energy's acceleration is not slowing down or reversing, it's increasing. Galaxies currently accessible, in principle, are being pushed beyond reach at an accelerating rate. Every year that passes, more galaxies cross the threshold from extremely difficult to reach to impossible to reach. There is no technology, no amount of energy, no clever physics that can overcome the expansion of space itself. From a practical standpoint, this means that if humanity wants to establish a presence beyond the Milky Way, our window of opportunity, already impossibly narrow from an engineering perspective, is actively closing. The universe is making the isolation of galaxies more severe with each passing moment. We are not just trapped in the Milky Way. The bars of our cosmic prison are actively closing in around us. Maintenance and repair, over million-year journeys, is impossible. Even if we solve the propulsion problem, the energy problem, the radiation problem, and all the other obstacles to intergalactic travel, we'd still face a challenge that might be the most intractable of all: keeping a spacecraft functional for millions of years. No human technology has ever operated reliably for even a tiny fraction of that time, and the engineering required to build something that could surpass current lifespans by factors of millions faces obstacles rooted in fundamental physics and materials science. The longest operating spacecraft in human history is Voyager 2, launched in 1977. As of 2025, it has been operating for approximately 48 years, a remarkable achievement. But Voyager is a simple probe with no crew, minimal systems, and low power requirements. It has already experienced multiple system failures, including the loss of its primary radio receiver, various instrument failures, and degradation of its power supply. Its radioisotope thermoelectric generators are slowly decaying, producing less power each year. Engineers predict Voyager's systems will fail completely by the 2030s, giving it a total operational life of about 60 years. 60 years is 0.000024% of a million years. An intergalactic journey to Andromeda, even at an impossible 90% of light speed, would take about 2.8 million years from Earth's perspective. The spacecraft would need to operate reliably for a duration 46,000 times longer than Voyager's expected lifetime. Nothing humans have ever built approaches this level of longevity. Every component of a spacecraft degrades over time. Metals fatigue from thermal cycling and microvibration. Plastics and composites break down from radiation exposure, losing strength and flexibility. Electronic components suffer from radiation damage, thermal stress, and simple wear. Even in the hard vacuum of space, materials' sublime molecules slowly escape from surfaces, gradually eroding components. Seals and gaskets harden and crack. Lubricants evaporate or degrade chemically. Coatings and insulation materials deteriorate. The radiation environment of deep space accelerates this degradation. Cosmic rays cause displacement damage in crystalline materials, gradually destroying the ordered structure that gives metals and semiconductors their properties. Electronics are particularly vulnerable. Transistors in computer chips accumulate defects over time, eventually failing. Memory storage degrades as radiation flips bits and damages storage media. obstacles rooted in fundamental physics and materials science. The longest operating spacecraft in human history is Voyager 2, launched in 1977. As of 2025, it has been operating for approximately 48 years, a remarkable achievement. But Voyager is a simple probe with no crew, minimal systems, and low power requirements. It has already experienced multiple system failures, including the loss of its primary radio receiver, various instrument failures, and degradation of its power supply. Its radioisotope thermoelectric generators are slowly decaying, producing less power each year. Engineers predict Voyager's systems will fail completely by the 2030s, giving it a total operational life of about 60 years. 60 years is 0.000024% of a million years. An intergalactic journey to Andromeda, even at an impossible 90% of light speed, would take about 2.8 million years from Earth's perspective. The spacecraft would need to operate reliably for a duration 46,000 times longer than Voyager's expected lifetime. Nothing humans have ever built approaches this level of longevity. Every component of a spacecraft degrades over time. Metals fatigue from thermal cycling and microvibration. Plastics and composites break down from radiation exposure, losing strength and flexibility. Electronic components suffer from radiation damage, thermal stress, and simple wear. Even in the hard vacuum of space, materials' sublime molecules slowly escape from surfaces, gradually eroding components. Seals and gaskets harden and crack. Lubricants evaporate or degrade chemically. Coatings and insulation materials deteriorate. The radiation environment of deep space accelerates this degradation. Cosmic rays cause displacement damage in crystalline materials, gradually destroying the ordered structure that gives metals and semiconductors their properties. Electronics are particularly vulnerable. Transistors in computer chips accumulate defects over time, eventually failing. Memory storage degrades as radiation flips bits and damages storage media. No electronic system has ever been tested for million-year reliability, because testing something for a million years is obviously impossible. Redundancy, having backup systems, helps, but only to a point. A spacecraft might carry 3 or 5 redundant copies of critical systems, but if each system has a 1% chance of failure per 1,000 years, having 10 redundant systems only extends expected life by a factor of 10. To achieve million-year reliability through redundancy alone would require thousands or millions of backup systems, each adding mass, complexity, and additional failure points. Self-repair mechanisms face fundamental limitations. A system capable of repairing itself would need to carry spare parts for every possible failure mode. It would need robotic manipulators capable of replacing or fixing any component. These repair systems would themselves be subject to failure, and would need their own redundancy and spare parts. The mass of tools, spare parts, and repair robots required for million-year self-sufficiency would be enormous. Some have proposed using nanotechnology or advanced AI to enable truly autonomous self-repair, but these technologies face their own limitations. Nanomachines would need power supplies, control systems, and raw materials. They would be subject to the same radiation damage and wear as larger systems. An AI capable of diagnosing and repairing arbitrary failures would need to be sophisticated enough to essentially redesign the spacecraft on the fly, a level of artificial general intelligence we're nowhere near achieving, and which itself raises questions about long-term stability and goal preservation over millions of years. Material science offers no solution to these problems. There are no materials that don't degrade over sufficient time. Even diamond, one of the hardest materials known, undergoes radiation damage and can be eroded by high-energy particle impacts. Gold, sometimes proposed for space applications due to its corrosion resistance, is soft and subject to displacement damage from cosmic rays. Every material we know eventually fails given enough time and exposure. The temperature problem in the void between galaxies. Thermal management in space is already a significant engineering challenge, but the environment of intergalactic space creates thermal problems that border on unsolvable for multi-million-year journeys. The temperature of empty space, far from stars and galaxies, is not absolute zero but rather the temperature of the cosmic microwave background, 2.7 Kelvin, or about negative 270.45 degrees Celsius. Maintaining appropriate temperatures for human life and sensitive equipment in this environment requires constant energy expenditure. Spacecraft generate heat from various sources: human metabolism, electronics, propulsion systems, and radioactive decay in power supplies. In the vacuum of space, this heat cannot be shed through conduction or convection, only through thermal radiation. The spacecraft must radiate away all generated heat, or its temperature will rise until the rate of radiation equals the rate of heat generation. The Stefan-Boltzmann law governs thermal radiation. The power radiated increases with the fourth power of absolute temperature. A warmer object radiates much more efficiently than a cooler one. This creates a problem. Spacecraft systems and humans need to be kept warm, but the only way to shed heat is through surfaces at those same warm temperatures. The spacecraft needs large radiators surfaces designed to emit thermal radiation efficiently, but radiators add mass and present targets for micrometeorite impacts and radiation damage. For a generational ship carrying thousands of humans, the thermal management challenge becomes severe. A human being generates approximately 100 watts of heat through metabolism. A crew of 1,000 would generate 100 kilowatts just from their bodies. Add in life support systems, computers, lighting, food production, water recycling, and other essential systems, and total heat generation could easily exceed 1 megawatt. Over a million-year journey, the radiators needed to dissipate this heat would degrade from micrometeorite impacts and radiation damage, requiring constant replacement itself a source of additional heat from the work required. At relativistic speeds, additional thermal problems emerge from the cosmic microwave background. As discussed earlier, the CMB would be blue-shifted in the forward direction of travel, appearing as higher energy radiation that heats the front of the spacecraft. At 90% of light speed, the CMB temperature in the forward direction would be blue-shifted by a factor related to the Lorentz factor and the Doppler shift, potentially reaching temperatures of tens or even hundreds of Kelvin. The front of the spacecraft would be bathed in this radiation, creating a significant heating load that radiators would need to dissipate. Conversely, the rear of the spacecraft would see the CMB redshifted to even lower temperatures, approaching absolute zero. This creates thermal asymmetry. The front of the ship would be warmer than the rear. Managing this temperature gradient to prevent thermal stresses that could crack structural components would require sophisticated thermal control systems that, again, must function flawlessly for millions of years. Power generation compounds the thermal problem. Nuclear fission and fusion reactors produce vast amounts of waste heat. Typically, only about 30 to 40% of the energy released is converted to useful electrical power, with the remainder becoming heat that must be dissipated. A fusion reactor producing 100 megawatts of electrical power would generate 200 to 300 megawatts of waste heat. Radiating this away would require massive radiator arrays covering thousands of square meters, all of which would degrade over time and need replacement. The psychology of permanent exile cannot be overcome. Beyond the engineering obstacles, intergalactic travel faces a psychological barrier that may be insurmountable. The human mind was not designed for permanent separation from Earth and multi-generational journeys into an empty void. The psychological effects of such isolation would be severe and possibly catastrophic to mission success. Consider the experience of the first generation, those who leave Earth, knowing they will never return, never see their home planet again, except as an increasingly distant point of light. Research on isolated groups, Antarctic research stations, submarines, remote outposts, shows that even temporary isolation from broader society causes significant psychological stress. Depression, anxiety, interpersonal conflicts, and decreased cognitive performance are common even on 6-month missions with guaranteed return. An interstellar mission lasting decades or centuries would involve permanent exile. The travelers would know with certainty that they will die in space, that their children and grandchildren would die in space, that dozens of generations might live and die in a metal cylinder separated from nature, from weather, from the vast biological diversity of Earth, from everything humanity evolved to experience. The psychological impact of this knowledge would be profound. Studies of isolated communities show that social cohesion tends to break down over time without fresh inputs and connections to a broader society. Conflicts escalate. Grudges persist across generations. Without the moderating influence of a larger social context, small groups can develop dysfunctional dynamics, authoritarian power structures, ostracism of individuals, or fracturing into hostile factions. On Earth, Individuals who find themselves in toxic social situations can leave. On a generation ship, there is nowhere to go. The ship's population would need to be large enough to maintain genetic diversity and social complexity. Probably thousands of individuals minimum, but managing a community of thousands in a confined space for centuries presents staggering challenges. Every aspect of life would need to be regulated. Reproduction rates to prevent population explosions or crashes, resource allocation, conflict resolution, education, work assignments, governance. The social systems needed to manage all this would need to be robust enough to survive the death of every individual who designed them, to persist across cultural evolution and drift. Psychological screening and support would be essential but insufficient. No screening process can predict how individuals will respond to decades of confinement. Mental illness can develop even in people with no prior history. Treatment options in the closed environment of a spacecraft would be limited. Psychiatric medications would need to be synthesized on board, requiring chemical manufacturing capabilities. Severe mental illness requiring isolation or restraint would strain limited space and resources. The psychological impact on children born aboard the ship deserves special consideration. These individuals would have no choice in their situation. They would be born into confinement and exile without consent. They would grow up surrounded by the same walls, the same limited group of people, the same enclosed artificial environment. Earth would be a myth to them, a place described in videos and files but never experienced. The destination galaxy would be equally abstract, a distant goal they would never reach. Navigation errors across millions of light years would be fatal. Navigating across intergalactic distances presents challenges that make even the most precise human navigation systems look hopelessly crude. A tiny error in heading or velocity, imperceptible at the start of a journey, would be amplified over millions of light years into a missed distance of hundreds of thousands or millions of light years. There would be no course corrections available, the fuel required would be prohibitive, and the timescales involved would make corrections ineffective. Consider the precision required. Andromeda is about 2.5 million light-years away. To reach it with an acceptable missed distance, say, within 10,000 light-years, still an enormous volume to search for a specific destination. The initial heading would need to be accurate to within approximately 0.23 degrees. This might seem achievable, but consider that this heading must be established and maintained over the entire journey while travelling at relativistic speeds, through a space that's essentially empty of reference points. In interstellar navigation within the Milky Way, nearby stars provide excellent reference points. Pulsars, rapidly rotating neutron stars emitting regular pulses of radio waves, can serve as cosmic lighthouses, their precise timing allowing spacecraft to determine position and velocity. But in intergalactic space, pulsars in the Milky Way would fade from detectability relatively quickly. Pulsars in the destination galaxy would be too distant to be useful until very late in the journey. The spacecraft would need to rely on inertial navigation using accelerometers and gyroscopes to track every acceleration and rotation, integrating these over time to determine current velocity and position. But all sensors drift. Accelerometers accumulate small errors that grow over time. Gyroscopes precess. Over millions of years, these tiny errors would compound into enormous uncertainties about the spacecraft's true position and velocity. Even if the spacecraft could accurately determine its position and velocity, correcting course after significant time has passed would be prohibitively expensive in terms of fuel. The velocity of the spacecraft relative to the destination would be enormous, hundreds of thousands of kilometers per second if traveling at a significant fraction of light speed. Changing this velocity requires energy. A course correction of even 1% of the velocity would require accelerating or decelerating the entire mass of the spacecraft, consuming substantial fuel reserves. The motion of the destination galaxy introduces additional complications. Galaxies don't sit still, they move through space under the influence of gravitational attraction from other large-scale structures. Andromeda is moving toward the Milky Way at about 110 kilometers per second, but it also has motion in other directions due to the gravitational influence of the local group's overall motion toward the Virgo cluster and other large-scale flows. Predicting Andromeda's position millions of years in the future would require precise knowledge of these motions and the mass distribution of dark matter throughout the local group and beyond. Even small uncertainties in these measurements would propagate over time. If our estimate of Andromeda's transverse velocity is off by even 1 kilometer per second, a tiny error by astronomical standards, this error would accumulate to about 3,260 light-years over a 49 million-year journey. The spacecraft would miss its target by distances measured in thousands of light-years. The expansion of space adds another complication. During a multi-million-year journey to Andromeda, space itself would expand by a measurable amount. While the Milky Way and Andromeda are gravitationally bound, and thus not being separated by cosmic expansion, the calculation of trajectories would need to account for general relativistic effects in the expanding spacetime between galaxies. The mathematics becomes considerably more complex than simple Newtonian orbital mechanics. The destination might not exist when we arrive. A journey lasting millions of years carries another sobering risk. The destination itself might change or even cease to exist during the transit time. Galaxies are not static objects, but dynamic systems that evolve, collide, and transform over cosmological timescales. A spacecraft departing today with Andromeda as its target would arrive at a destination significantly different from the one its builders studied. Andromeda itself is on a collision course with the Milky Way. Current predictions suggest the two galaxies will begin their merger in approximately 4.5 billion years. But this is the beginning of the collision, not the end. The actual merger process takes billions of years, during which the galaxies will pass through each other multiple times, their shapes distorting, their spiral arms unraveling, their central black holes spiraling inward to eventually merge. A spacecraft departing for Andromeda today at 90% of light speed would arrive in about 8 million years. Andromeda would still be recognizable and distinct from the Milky Way, but a slower journey, or a trip to a more distant galaxy, might arrive to find the destination fundamentally transformed. A journey to a galaxy 100 million light-years away, even at 90% of light speed, would take about 111 million years. In that time, the destination galaxy could undergo major mergers with neighbouring galaxies, transform from a spiral to an elliptical, or have its structure dramatically altered by tidal interactions. The intended destination within the galaxy presents even greater uncertainty. If the goal were to reach a specific star system capable of supporting life, a planet orbiting a sun-like star in a stable orbit, the challenges multiply. Stars move through their galaxies on complex orbits that take hundreds of millions of years to complete. A target star system that looks promising today would have moved tens of thousands of light-years during a multi-million-year journey. Finding it again would be nearly impossible. Even if the target star remained identifiable, its planets might no longer be habitable. Stellar evolution, asteroid impacts, climatic shifts, or the natural evolution of a planet's geophysics and atmosphere could render a once promising world uninhabitable. Earth itself has undergone multiple mass extinctions, ice ages, and dramatic climate shifts over much shorter timescales than an intergalactic journey would require. The threat of gamma-ray bursts and supernovae adds another layer of risk. These events release enormous amounts of high-energy radiation capable of sterilizing nearby star systems. A gamma-ray burst occurring within 10,000 light-years of a destination star system would likely strip away planetary atmospheres and deliver lethal radiation doses to any life present. Over millions of years, the probability of such an event occurring near any given star system becomes non-negligible. There's also the possibility that the destination galaxy becomes gravitationally perturbed during the journey. A close passage by another large galaxy could trigger dramatic restructuring, flinging star systems into intergalactic space, triggering intense starbursts, or heating the interstellar medium to temperatures that would make planetary system formation difficult for millions of years afterward. The spacecraft would arrive in chaos rather than a stable environment for colonization. The communication lag makes mission control meaningless. Even if a spacecraft successfully launched on an intergalactic journey, the communication delays involved would make any kind of guidance, support, or even monitoring from Earth completely impossible. Light-speed communication lag has already proven challenging for Mars missions, where signals take between 4 and 24 minutes to travel one way depending on the planet's positions. For intergalactic missions, the lag becomes absurd. A spacecraft travelling to Andromeda would be 2.5 million light-years away at destination. Any radio signal sent from the spacecraft would take 2.5 million years to reach Earth. A reply from Earth would take another 2.5 million years to reach the spacecraft, a round-trip communication time of 5 million years. This isn't a communication delay, it's a communication impossibility. By the time a message from the spacecraft reached Earth, humanity might not exist. Human civilization as we know it is only about 10,000 years old. Modern humans have existed for roughly 300,000 years. 5 million years is 16 times longer than humans have existed as a species. The entity that receives a message from an intergalactic spacecraft would likely not be human in any sense we would recognize. It might be our evolved descendants, post-human AI entities, or nothing at all if humanity has gone extinct. From the spacecraft's perspective, Earth might as well not exist. Any message sent would be a message in a bottle cast into an ocean of time. There could be no expectation of reply, no possibility of requesting assistance, no chance of receiving updated information or instructions. The spacecraft and its occupants would be completely autonomous from the moment of departure, cut off from humanity forever. This isolation has profound implications for mission design and decision-making. Traditional spaceflight relies on ground controllers who monitor telemetry, diagnose problems, and send solutions. The Apollo 13 mission succeeded because engineers on Earth could analyze the failure, devise a solution using available materials, and communicate instructions to the crew. An intergalactic spacecraft would have no such support. Every problem would need to be solved by the crew and onboard systems with no outside help. The psychological impact of this communication isolation compounds the other psychological challenges discussed earlier. The crew would know with certainty that they cannot call for help, cannot receive news from home, and cannot even expect their messages to be received by anyone who remembers them. They would be speaking to the distant future, to descendants so remote in time that they might as well be aliens. Gravity assist maneuvers are impossible between galaxies. In interplanetary spaceflight, gravity assist maneuvers have proven invaluable for changing spacecraft velocity without expending fuel. A spacecraft approaching a planet on a carefully calculated trajectory can use the planet's gravity to alter its speed and direction, effectively stealing a small amount of the planet's orbital energy. This technique has enabled missions like Voyager to visit multiple planets and eventually leave the solar system. Gravity assists work because planets are massive, move at high velocities, and are conveniently spaced throughout the solar system. Careful mission planning can string together multiple assists to reach destinations that would otherwise require prohibitive amounts of fuel, but intergalactic space lacks the necessary infrastructure for this technique. Between galaxies, there are essentially no massive bodies to use for gravity assists. The intergalactic medium is extraordinarily diffuse, a few atoms per cubic meter at most. Dwarf galaxies orbiting between larger galaxies might seem like potential candidates, but they're too small and too sparse to provide useful gravitational boosts over the enormous distances involved. Even if suitable massive objects existed along the route, the timescales make gravity assists impractical. A gravity assist around a star or planet takes days to weeks. A gravity assist around a galaxy would take millions of years. The spacecraft would need to enter the galaxy's gravitational influence, swing around its center, and exit along a different trajectory. This maneuver would add millions of years to an already multi-million-year journey, and the velocity change achieved would likely be small compared to the spacecraft's initial velocity. The absence of gravity assists means that a spacecraft must carry all the energy needed for the entire journey. It must accelerate to cruising velocity using onboard fuel, coast for millions of years, and then decelerate to arrive at the destination. There are no opportunities to top up velocity or adjust course using gravitational interactions. Every joule of energy must come from fuel carried at launch, or generated by onboard power systems. This requirement drives the energy problem to truly absurd extremes. As discussed earlier, the energy needed to reach relativistic velocities is enormous even for small masses. Without gravity assists or other means of gaining energy during flight, the fuel requirements become prohibitive to the point of impossibility. The biological problem. Humans cannot survive multi-million-year journeys. Even setting aside all the engineering challenges, there's a fundamental biological problem. Humans are mortal. A single human lifespan is measured in decades, not millions of years. Any intergalactic journey would necessarily be a multi-generational undertaking, and maintaining a viable human population over thousands of generations in a closed spacecraft presents biological challenges that may be insurmountable. genetic diversity is essential for population health. Small, isolated populations suffer from inbreeding, which increases the frequency of harmful recessive genes and reduces the population's ability to adapt to new challenges. On Earth, conservation biologists estimate that populations smaller than a few hundred individuals face long-term extinction risk due to inbreeding and genetic drift. A generation ship would need to carry at least 500 to 1,000 individuals to maintain sufficient genetic diversity over thousands of generations, but even this might not be enough. Computer simulations of isolated populations over extremely long time spans show that genetic drift, random changes in gene frequency, inevitably reduces diversity over time, even in the absence of inbreeding. After thousands of generations, the population would likely suffer from accumulated genetic load, an increasing burden of mildly harmful mutations that reduce fitness. Radiation exposure compounds this problem. As discussed earlier, cosmic rays damage DNA. While individual cells can repair some of this damage, errors in repair introduce mutations. Over thousands of generations, exposed to cosmic ray flux far higher than Earth-based populations experience, the generation ship population would accumulate mutations at an accelerated rate. Some of these mutations would be neutral, but others would be harmful, increasing cancer risk, reducing fertility, and causing various genetic diseases. Maintaining Earth-level gravity throughout the spacecraft is essential for human health, but doing so requires constant rotation, which creates engineering challenges and mechanical stresses. If the artificial gravity system failed, even temporarily, the crew would experience rapid bone density loss and muscle atrophy. Long-term exposure to microgravity causes permanent physiological changes, including fluid redistribution, vision problems, and immune system dysfunction. Recovery from extended microgravity exposure is incomplete, and multi-generational exposure could lead to permanent adaptation to microgravity, leaving descendants unable to function in Earth normal gravity, even if they eventually reached a habitable planet. The closed environment of a spacecraft also poses biological risks. On Earth, humans are exposed to an enormous diversity of microorganisms, most of which are harmless or beneficial. Our immune systems evolved in this environment and require exposure to diverse microbes for proper development. A generation ship would have a severely limited microbiome, only the microbes present in the original crew and those necessary for food production and waste recycling. Over time, this limited microbial ecosystem could drift into configurations that are harmful to human health, or the human immune system could become hypersensitive or immunodeficient due to lack of proper stimulation. Our prison is also our garden. The sobering reality of cosmic isolation carries with it a strange comfort. We cannot leave the Milky Way, not because of any failure of imagination or ambition, but because the universe itself has written laws that forbid it. The barriers aren't technological, they're written into the fabric of reality. The speed of light, the expansion of space, the vast emptiness between galaxies, and the enormous energies required to cross such distances. These aren't obstacles to overcome, but fundamental features of the cosmos we inhabit. This means that our galaxy, vast beyond comprehension, is our permanent home. The Milky Way contains somewhere between 200 and 400 billion stars. Current estimates suggest at least 20% of Sun-like stars have Earth-sized planets in their habitable zones, implying billions of potentially habitable worlds within our galaxy alone. We have not one planet but potentially billions to explore, terraform, and settle. The intergalactic frontier is so vast that humanity could expand for millions of years without exhausting the possibilities within the Milky Way. The physical impossibility of intergalactic travel also means we'll likely never encounter alien civilizations from other galaxies. If the barriers that trap us here apply to all matter-based life forms, then every advanced civilization in the cosmos is similarly confined to its home galaxy. The Milky Way may be home to other intelligent species, but if so, we're all prisoners together, which creates a shared context. Any species we encounter would face the same fundamental limitations we do. This confinement might actually increase our chances of long-term survival. The universe is vast and dangerous on the largest scales. Gamma-ray bursts, galactic collisions, and other catastrophic events occur regularly across cosmic distances. By being confined to the Milky Way, we're also limited in our exposure to galaxy-scale threats from other regions of the universe. Our prison is also our shelter. The laws of physics that confine us within the Milky Way are the same laws that make stable matter possible, that allow stars to shine steadily for billions of years, that permit the chemistry of life. We cannot escape the Milky Way precisely because we are creatures made of matter and energy, bound by the same physical laws that create the structure and stability necessary for our existence. Our prison is not separate from us, it is part of us, and we are part of it. The galaxy that holds us captive is not a cell but a garden, vast enough to contain wonders beyond counting. Its spiral arms shelter billions of stellar systems, its dust lanes hide nurseries where new stars are born. Its ancient halo contains fossils of the universe's youth. This is not a small cage but a cosmic domain 100,000 light-years across, with enough diversity and possibility to challenge and fascinate us for as long as we persist as a species. We are trapped in paradise, bound to a realm of such magnificence that exploring its full extent would take civilizations millions of years. The Milky Way is our prison, our home, our future, and our fate. And in the end, that may be exactly what it should be. The Andromeda collision demonstrates galactic imprisonment. In approximately 4.5 billion years, the Milky Way and Andromeda galaxies will collide in a slow-motion cosmic crash that will fundamentally restructure both galaxies. This impending merger, far from offering an opportunity for humanity to expand its reach, actually demonstrates the absolute nature of our galactic imprisonment. Even when two galaxies merge, becoming one, the fundamental barriers to intergalactic travel remain unbreached. Current observations, primarily from the Hubble Space Telescope and Gaia mission, have tracked Andromeda's motion through space with remarkable precision. The galaxy is approaching the Milky Way at approximately 110 kilometers per second, about 250,000 miles per hour. Its light shows a blue shift rather than the red shift typical of distant galaxies, confirming that Andromeda and the Milky Way are gravitationally bound and approaching despite the expansion of space. Computer simulations of the merger, incorporating our current understanding of galactic dynamics and dark matter distributions, reveal a complex dance spanning several billion years. The first close passage will occur in approximately 4.5 billion years, but the galaxies won't immediately merge. Instead, they'll swing past each other, their mutual gravity distorting both structures and flinging long tidal tails of stars into intergalactic space. These tails, stretching hundreds of thousands of light-years, will be spectacular from a distance but represent stars permanently ejected from both galaxies. After the first passage, the galaxies will separate, slowed by their mutual gravitational interaction. Over the next billion years, they'll reach maximum separation, perhaps 500,000 light-years apart, before falling back together for a second collision. This pattern will repeat several times, each passage further disrupting both galaxies' spiral structures. After perhaps 3 or 4 such collisions over the course of about 3 billion years, the galaxies will have lost enough kinetic energy to their tidal interactions that they'll finally merge into a single elliptical galaxy. Astronomers have nicknamed Milkomeda or Milkdromeda. During these billions of years of collision and merger, one might imagine that opportunities would arise for travel between the galaxies. When they first approach, the distance between the nearest stars of each galaxy might be only tens of thousands of light-years, far less than the current 2.5 million light-year separation. Surely this would make intergalactic travel easier. But the answer remains no, for multiple reasons. First, tens of thousands of light-years still represents an insurmountable barrier given the constraints on energy, propulsion, and travel time we've discussed. A journey of 50,000 light-years at 90% light speed still requires about 55,000 years from Earth's perspective, and subjects travelers to all the radiation, maintenance, and psychological challenges of extended spaceflight. Second, during the collision, both galaxies will be undergoing violent restructuring. The tidal forces will fling stars into chaotic, high-velocity orbits. The interstellar medium will collide, compressing gas clouds and triggering massive bursts of star formation. Many regions will be bathed in intense ultraviolet and X-ray radiation from newly formed massive stars. The radiation environment will be far more hazardous than it is now, making travel even more dangerous. Third, the relative velocities involved create additional problems. As the galaxies pass through each other, stars from one galaxy will be moving at hundreds of kilometers per second relative to stars in the other. A spacecraft attempting to transfer from the Milky Way to Andromeda during a close passage would need to match this velocity change, requiring energy expenditure equivalent to accelerating to hundreds of kilometers per second, decelerating, then accelerating again. This isn't merely cruising to a destination, it's jumping between two massive objects moving at high speed relative to each other. The merger of supermassive black holes at the centers of both galaxies creates another hazard. Sagittarius A star, the Milky Way's central black hole at 4 million solar masses, and Andromeda's central black hole, estimated at 100 to 200 million solar masses, will eventually spiral together and merge. This process will emit gravitational waves carrying enormous energy. While gravitational waves interact weakly with matter, making them safe at most distances, the regions near the inspiraling black holes will be deadly. Intense tidal forces and high-energy radiation from superheated gas swirling into both black holes will make the central regions of the merging galaxies uninhabitable for millions of years. Perhaps most significant is what the merger demonstrates about the nature of galactic boundaries. Even as the two galaxies merge, becoming one, the vast majority of their volumes remain empty. The stars of the Milky Way and Andromeda will mostly pass by each other without colliding, because the distances between stars are so vast compared to stellar sizes. Two ships passing in the night through the same space, their components never touching. This reveals a profound truth. Galaxies aren't objects with hard boundaries, but diffuse clouds of gravitationally bound stars, gas, and dark matter. The merger is really just the intermingling of two such clouds. There's no moment when one can say, now we're in Andromeda instead of the Milky Way, because the transition is gradual and ill-defined. The imprisonment isn't about physical barriers, but about gravitational binding and cosmic distances. After the merger completes, perhaps 7 billion years from now, Milky will contain nearly all the stars from both progenitor galaxies, over 1 trillion stars in total. This expanded galaxy will be larger than either of its predecessors, potentially stretching 200,000 light-years or more across. One might argue that this gives humanity a larger prison to inhabit, but this misses the point. The merger doesn't expand our accessible universe. It merely demonstrates that even galaxy-scale transformations cannot overcome the fundamental barriers to intergalactic travel. During billions of years of collision, merger, and restructuring, the most dramatic possible astronomical event, short of a nearby gamma-ray burst or supernova, the obstacles to moving between galaxies remain absolute. Moreover, Milky itself will remain a prison. After the merger, the nearest large galaxies will be the members of the local group Triangulum, if it hasn't already been absorbed, and various dwarf galaxies. Beyond the local group, all other galaxies will be receding due to cosmic expansion. By the time Milky forms, perhaps 7 billion years from now, the expansion of space driven by dark energy will have carried most galaxies beyond the cosmic horizon, making them forever unreachable even if we could somehow travel at light speed. Cosmic expansion will eventually erase all evidence of other galaxies. The accelerating expansion of the universe driven by dark energy isn't just a barrier to intergalactic travel. It will eventually hide the very existence of other galaxies from future observers. In a cosmic timescale measured in hundreds of billions of years, the universe will undergo a transformation so complete that civilizations arising in the far future will be unable to discover that galaxies beyond their own ever existed. This represents the ultimate form of cosmic imprisonment, not just being unable to reach other galaxies, but being unable to even know they exist. Current measurements of cosmic expansion, primarily from observations of Type Ia supernovae, cosmic microwave background anisotropies, and baryon acoustic oscillations, indicate that the expansion rate is increasing over time. The Hubble constant, the rate of expansion per unit distance, isn't actually constant, but increases as the universe ages. This acceleration is attributed to dark energy, which makes up approximately 68% of the universe's total energy density. The key property of dark energy, assuming it behaves as a cosmological constant, is that its density remains unchanged as the universe expands. Unlike matter, which becomes more dilute as space stretches, dark energy maintains constant energy per unit volume. This means that as the universe grows, the total amount of dark energy increases proportionally. More dark energy means stronger acceleration, creating a runaway feedback effect, Projecting this forward, cosmologists can calculate how the observable universe will evolve. Currently, we can observe galaxies out to distances of about 46.5 billion light-years in all directions, despite the universe being only 13.8 billion years old. This is because space itself has expanded during the time light was travelling to us, stretching the distance to distant light sources. But the accelerating expansion means that the observable universe will actually shrink in the future, in a practical sense. Galaxies currently visible will be carried away by expansion faster than their light can reach us. Their light will be redshifted to longer and longer wavelengths, eventually stretching beyond the range of any conceivable detector. These galaxies won't disappear instantaneously but will fade gradually, becoming dimmer and redder until they vanish from view entirely. The timescale for this process depends on distance. Galaxies in the Virgo cluster, about 54 million light-years away, will remain visible for hundreds of billions of years, but more distant galaxies are already in the process of fading. Galaxies at redshift Z is greater than 1.8, corresponding to distances where the light we see was emitted more than 10 billion years ago, are already receding faster than the speed of light due to the expansion of space. We can still see them because the light was emitted when they were closer, but we could never reach them even at light speed because space is expanding too rapidly. Computer simulations tracking the future evolution of the local group and the universe at large paint a stark picture. In approximately 150 billion years, every galaxy beyond the local group will have receded beyond the cosmic event horizon. The merged Milky Way galaxy, along with the Triangulum galaxy if it hasn't merged with us, and our various dwarf satellite galaxies will constitute the entire observable universe. Beyond this local system, the sky will appear completely empty of galaxies. But the isolation goes deeper. The cosmic microwave background, the faint afterglow of the Big Bang that currently fills the sky at microwave wavelengths, will also fade from view. This radiation has already been stretched from visible light at the time of emission, 13.8 billion years ago, to microwaves today. Continued expansion will stretch it further into radio waves, then longer wavelengths, until its temperature drops effectively to zero. In 150 billion years, the CMB will be undetectable even with perfect instruments. This means that future civilizations, whether our descendants or alien species evolving billions of years from now, will have no observational evidence for the Big Bang. They won't be able to detect the CMB. They won't see distant galaxies. They won't observe the large-scale structure of the universe. From their perspective, the universe will appear to consist only of their local galactic system surrounded by infinite empty space. Without the CMB and distant galaxies, these future civilizations won't be able to measure cosmic expansion. They'll have no way to determine that space itself is expanding. They might develop sophisticated physics and astronomy, but their observations would be consistent with a static, eternal universe consisting only of their galaxy and its satellites. They would have no way to discover that the universe had a beginning, that it's expanding, or that other galaxies ever existed. This has profound implications for the nature of scientific knowledge. Some cosmologists have pointed out that we happen to live in a special era, a golden age of cosmology, when the evidence for the Big Bang and cosmic expansion is abundant and relatively easy to detect. If humanity had evolved just 100 billion years later, we might never have discovered these fundamental facts about the universe. This suggests a disturbing possibility. There might be important truths about the universe that are in principle impossible for us to discover because we don't live in the right epoch. Just as future civilizations will be unable to observe the evidence for cosmic expansion and the Big Bang, there might be phenomena in the universe's past or future that would reveal crucial insights, but whose evidence has already faded or hasn't yet appeared. The accelerating expansion will also affect our ability to study cosmology even before other galaxies disappear from view. The most distant galaxies, the ones we observe at high redshifts, whose light has been travelling for most of the age of the universe, provide crucial information about the universe's early history and evolution. But these galaxies are already fading. In a few 100 billion years, we would lose our window into the universe's first billion years. The expansion will even affect measurements of fundamental constants. Some physicists have proposed that certain constants might vary very slowly over cosmic time. Testing such hypotheses requires comparing measurements from different cosmic epochs, studying distant galaxies whose light was emitted billions of years ago, and comparing their spectra to laboratory measurements today. Once those distant galaxies fade beyond detection, we'll lose the ability to perform these tests, potentially forever closing certain lines of inquiry. From a philosophical perspective, the eventual erasure of evidence for other galaxies represents the ultimate isolation. We're not just imprisoned within the Milky Way by practical barriers. The universe is actively hiding the existence of the wider cosmos from future observers. It's as if the universe is drawing curtains around our local group, slowly but inexorably reducing our cosmic context to just our immediate galactic neighborhood. This erasure also has implications for the Fermi paradox, the question of why we haven't detected signs of alien civilizations. If advanced civilizations billions of years older than ours exist, they might already be living in a universe where they can observe only their local galaxy group. They would have no way to know we exist and no means to detect our signals or visit us, even if they suspected we were here. The universe's expansion effectively partitions all civilizations into isolated pockets, each unaware of the others. The collapse of technological optimism about interstellar travel. For decades, popular culture and even some serious scientists have promoted a narrative of inevitable technological progress that would eventually overcome any barrier to space exploration. This optimism, rooted in the rapid technological advances of the 20th century, suggests that given enough time and ingenuity, humanity will develop the capabilities to travel to other stars and even other galaxies. But a sober examination of physics reveals this optimism is fundamentally misplaced. Some barriers cannot be overcome by technology because they're not technological limitations, they're consequences of natural law. The mythology of inevitable progress traces back to the dramatic technological leaps of the past 2 centuries. In 1800, the fastest way to travel was on horseback, at speeds of perhaps 30 to 40 kilometers per hour. By 1900, trains reached speeds over 160 kilometers per hour. By the 1960s, humans had reached the moon, and by the 1970s, the Voyager probes were on their way out of the solar system. This exponential progression created an expectation that similar leaps would continue indefinitely. Science fiction reinforced this expectation. Authors like Isaac Asimov, Arthur C. Clarke, and Robert Heinlein imagined futures where interstellar travel was routine, where humanity established colonies among the stars within centuries. Star Trek depicted a future where faster-than-light warp drive made intergalactic travel possible. These visions were inspiring, but they were fiction, not projections based on actual physics. The critical mistake in extrapolating past progress to future capabilities is assuming that all barriers are technological. The progression from horses to spacecraft represents overcoming engineering challenges and energy limitations, difficult problems, but solvable with sufficient ingenuity and resources. We developed internal combustion engines, rocket propulsion, and eventually ion drives. Each advance required better materials, more sophisticated engineering, and more concentrated energy sources, but none required changing the laws of physics. But the barriers to intergalactic travel aren't in the same category. The speed of light isn't an engineering constraint that better technology can overcome. It's a fundamental feature of space-time geometry. Einstein's special relativity shows that as an object with mass accelerates toward light speed, its energy requirements approach infinity. You could harness the energy output of an entire star for centuries and still not accelerate even a kilogram to light speed. This isn't a materials problem or an engineering problem, it's a mathematical consequence of how space and time are structured. Similarly, the expansion of space driven by dark energy isn't something that better propulsion systems can overcome. Space itself is stretching, carrying distant galaxies away from us faster than light can travel. No propulsion system, no matter how advanced, can overcome this, because the destination is receding faster than you can approach it. It's like running on a treadmill that accelerates faster than you can run. No amount of training or better running shoes will let you reach the end if it's moving away faster than you can move forward. The Breakthrough Starshot project, announced in 2016 with backing from physicist Stephen Hawking and investor Yuri Milner, illustrates both the ambition and the limitations of current thinking about interstellar travel. The project proposes using ground-based lasers to accelerate tiny spacecraft, essentially computer chips with light sails to 20% of light speed, enabling them to reach Proxima Centauri in about 20 years. Even if successful, Breakthrough starshot would demonstrate the limitations rather than the possibilities of interstellar travel. The spacecraft would be tiny, just a few grams, and would carry essentially no payload beyond basic sensors and a communication system. They couldn't slow down upon arrival, so they would flash past Proxima Centauri in hours, gathering data during a brief flyby. The communication time back to Earth would be 4.2 years, during which the probes would be long gone from the star system. Scaling this approach to carry humans is essentially impossible. A spacecraft large enough to carry even a single human would mass millions of times more than the chip-scale probes. The laser power requirements would scale proportionally, requiring perhaps trillions of watts of continuous power focused to extraordinary precision across trillions of kilometers. The engineering challenges of such a system are formidable, but even setting those aside, the energy requirements are staggering, more than the current total power consumption of human civilization, sustained for years, and this would only get humans to Proxima Centauri, the nearest star. Andromeda, at 2.5 million light-years, is 590,000 times farther away. Even if we could somehow achieve 20% light speed for a crewed mission, the journey would take 12.5 million years. The laser-based approach doesn't scale. It's fundamentally limited to tiny probes on one-way missions to nearby stars. Some have proposed using fusion drives, antimatter propulsion, or even more exotic concepts, but each faces fundamental limitations rooted in physics. Fusion, the most energetically favorable reaction aside from antimatter annihilation, releases about 0.7% of the mass energy of fuel as usable energy. Even with perfect efficiency impossible due to thermodynamics, you'd need hundreds of times more fuel than payload to reach relativistic speeds. The tyranny of the rocket equation means that for any given exhaust velocity, there's a limit to how fast you can accelerate. Antimatter offers the maximum possible energy density, complete conversion of mass to energy. But antimatter doesn't exist naturally in any significant quantity. Every antiparticle must be manufactured, and current production rates measure in nanograms per year. The energy required to produce antimatter is greater than the energy you get from annihilating it, making it not a fuel source but an energy storage medium, and an extraordinarily inefficient one. Even if we could somehow scale up production by factors of billions, we'd need to dedicate the energy output of multiple stars just to produce enough antimatter for a single intergalactic mission. The optimistic narrative often invokes unknown physics. We don't know what we don't know, and physics in the future might reveal new possibilities. But this hope is misplaced for several reasons. First, our current physical theories are extraordinarily well tested in the regimes relevant to spaceflight. Special relativity has been verified to extraordinary precision in particle accelerators, where particles routinely reach 99.9999% of light speed. General relativity has been confirmed by observations ranging from GPS satellites to gravitational wave detections. The standard model of particle physics explains the behavior of matter at energy scales far higher than anything relevant to propulsion. Second, the gaps in our current physics, things like quantum gravity and the nature of dark matter and dark energy, exist at scales, and in regimes that are unlikely to provide loopholes for faster-than-light travel. Quantum gravity becomes important at the Planck scale. Distances of about 10, -35 meters, and energies of about 10, 19 GeV conditions that existed only in the first moments after the Big Bang, and in the centers of black holes. There's no reason to expect quantum gravity effects to manifest in ways that would help spacecraft traveling through normal space at normal energy scales. The Fermi paradox solved. Everyone is trapped in their galaxy. The Fermi paradox, the apparent contradiction between the high probability of alien civilizations existing and the complete absence of evidence for them, has puzzled scientists for decades. Physicist Enrico Fermi famously asked, "Where is everybody?" when discussing the likelihood of extraterrestrial intelligence. If intelligent life is common in the universe, and if technological civilizations inevitably develop space travel, then even allowing for slow expansion at sublight speeds, the entire galaxy should have been colonized millions of years ago, yet we see no evidence of alien civilizations anywhere. Numerous solutions to the Fermi paradox have been proposed. Perhaps intelligence is extremely rare. Perhaps civilizations self-destruct. Perhaps aliens exist but are hiding. Perhaps they're here but undetected. But there's a simpler explanation that follows directly from the physics we've been discussing. Everyone is trapped in their home galaxy, just as we are, and intergalactic communication is impossible. Consider the observable universe, which contains approximately 2 trillion galaxies within 46.5 billion light-years. If even a small fraction of these galaxies contain intelligent life, there could be millions or billions of technological civilizations in the cosmos. But if each civilization is confined to its home galaxy by the fundamental barriers we've discussed, then the universe is partitioned into trillions of isolated pockets, each completely cut off from all the others. This partition is absolute. No signals travel between galaxies in any useful time frame. A radio transmission from Andromeda takes 2.5 million years to reach the Milky Way. By the time we receive such a signal, the civilization that sent it would likely have evolved beyond recognition or gone extinct. Any reply we sent would take another 2.5 million years to arrive. This isn't communication in any meaningful sense, it's sending messages to the distant future with no possibility of conversation. For more distant galaxies, communication becomes even more impossible. The expansion of space means that galaxies beyond a certain distance are receding faster than light. Signals from these galaxies can never reach us, and our signals can never reach them. We're not just separated by distance, but by the structure of space-time itself. We occupy different causal patches of the universe regions that can never influence each other. This resolves the Fermi paradox completely for intergalactic civilizations. We shouldn't expect to detect aliens from other galaxies, because communication across intergalactic distances is physically impossible. The universe is full of civilizations, but they're partitioned into galaxy-sized prisons, each evolving in isolation, each unaware of the others. But what about civilizations within our own galaxy? The Milky Way contains 200 to 400 billion stars and potentially billions of habitable planets. If intelligent life arose on even a tiny fraction of these, there should be thousands or millions of civilizations within the Milky Way alone. Even if interstellar travel is difficult, surely some of these civilizations would have established detectable presence over millions of years. Yet we observe no evidence of extraterrestrial civilizations in the Milky Way. The search for extraterrestrial intelligence, SETI, has been monitoring radio frequencies for decades, looking for artificial signals. Sky surveys have searched for signs of megastructures like Dyson spheres that advanced civilizations might build. We found nothing, no signals, no artifacts, no evidence of large-scale engineering projects, no visits to Earth by alien spacecraft. Several factors might explain this silence. First, the timescales involved are enormous. Even if an advanced civilization arose on the opposite side of the Milky Way and sent signals in all directions, those signals would take 80,000 years to reach us at light speed. If they arose 100,000 years ago, their signal might still be in transit. If they arose 200,000 years ago, their signal passed Earth before humans existed to detect it. The window for detecting civilizations is surprisingly narrow when considered against cosmic timescales. Second, interstellar travel may be so difficult that even advanced civilizations don't attempt it. The energy requirements, as we've discussed, are staggering. A civilization might calculate that the resources required to send even a single colony ship to another star would be better spent improving life on their home world and in their home star system. The cost-benefit analysis of interstellar colonization might make it unappealing, even if it's technically possible. Third, civilizations might be short-lived compared to stellar lifetimes. Technological civilization on Earth is only about 200 years old, a blink of an eye compared to the Sun's 4-6 billion-year age. If most civilizations last only thousands or tens of thousands of years before collapsing or transforming into something unrecognizable, then at any given moment, only a tiny fraction of potential civilizations are actually transmitting detectable signals. The galaxy might be full of ruins and remnants, but empty of active, communicating civilizations. Fourth, the assumption that advanced civilizations would want to communicate or expand might be wrong. Human motivations and behaviors might not be universal. An alien civilization could develop technology advanced enough for interstellar communication but lack any interest in doing so. Their psychology, their values, their conception of meaning and purpose might be so alien that behaviors we consider obvious exploring, communicating, expanding never occur to them. The combination of these factors within galaxies and the absolute barrier between galaxies suggests a universe full of life but also full of silence. Each galaxy is a cosmic island, potentially containing thousands or millions of civilizations, but isolated from all other galaxies by insurmountable physics. Within each galaxy, civilizations arise, flourish briefly and fade, rarely or never making contact with each other due to the vast distances, the timing challenges, and possibly the sheer difficulty of interstellar travel and communication. This picture is lonely but also profound. It suggests that the universe is not empty of intelligence, but rather that intelligence is fragmented into countless isolated instances, each experiencing the cosmos from its unique perspective, each developing its own understanding of reality, each asking the same questions we ask, but never able to share answers across the void. For humanity, this means our efforts to search for extraterrestrial intelligence should focus on our local cosmic neighborhood, perhaps within a few thousand light years where signals could be detected within historical timeframes and where the possibility of eventual contact, however remote, exists. Searching for signals from other galaxies, or even from the far side of our own galaxy, is probably futile, not because no one is there, but because the physics of communication across such distances makes meaningful contact impossible. The quantum limits on information transfer seal our isolation. Beyond the classical physics barriers of speed and distance, quantum mechanics imposes additional fundamental limits on information transfer that guarantee our cosmic isolation. These limits arise not from engineering challenges but from the inherent nature of information itself at the quantum level, creating barriers that no technology, regardless of how advanced, can overcome. The quantum no-cloning theorem, proven by physicists William Wouters and Wojciech Zurek in 1982, states that it's impossible to create an identical copy of an arbitrary unknown quantum state. This isn't a technological limitation, it's a fundamental consequence of the linearity of quantum mechanics. The implications for information transfer across cosmic distances are profound and deeply constraining. Consider a civilization attempting to send detailed information about itself across intergalactic space. Quantum information, the complete quantum state of particles and systems, cannot be perfectly copied. If you want to transmit quantum information from one location to another, you must physically transport the quantum system itself, or you must use quantum teleportation, which requires a pre-established entangled pair of particles shared between sender and receiver. Quantum teleportation sounds promising at first. In 1993, Charles Bennett and colleagues showed theoretically that quantum information could be transferred between two locations using quantum entanglement, without the information traveling through the space between. This has been experimentally demonstrated over distances of hundreds of kilometers on Earth, and even from satellites to ground stations. But the process has strict requirements that make it useless for intergalactic communication. Quantum teleportation requires three things. First, an entangled pair of particles where one particle is with the sender and one with the receiver. Second, the quantum system to be teleported. And third, a classical communication channel through which the sender transmits measurement results to the receiver. This classical channel is crucial. Without it, the receiver cannot complete the teleportation process, and this classical channel is limited by the speed of light. This means quantum teleportation doesn't enable faster-than-light communication. The quantum information isn't transmitted faster than light. It's reconstructed at the destination based on the entangled pair and classical information about measurement results. The classical information must travel from sender to receiver at light speed or slower, so the overall process is still limited by relativity. For intergalactic communication, this is fatal. To teleport quantum information from the Milky Way to Andromeda, you would need to first establish entangled particle pairs between the two galaxies. But distributing these entangled particles requires physically transporting them across intergalactic space, which takes millions of years at best. Once the entanglement is established, you still need the classical communication channel, which introduces 2.5 million years of delay. Quantum teleportation offers no advantage over simply sending the information classically. Quantum entanglement itself, often misunderstood in popular science, doesn't allow faster-than-light communication. When two particles are entangled, measuring one particle's state instantly determines the other particle's state, regardless of distance. This spooky action at a distance, as Einstein called it, seems to suggest instantaneous information transfer, but it doesn't. The key issue is that the measurement results are random until measurement occurs. If Alice measures her entangled particle and gets the result up, she instantly knows Bob's particle will measure down. But Bob, measuring his particle without communication from Alice, simply gets a random result. He has no way of knowing whether his result is correlated with Alice's measurement or is just random noise. Only when Alice sends Bob a classical message limited to light speed describing her measurement can Bob confirm the entanglement and extract any information from it. This is formalized in the quantum no-communication theorem, which proves that quantum entanglement cannot transmit information faster than light. Any attempt to use entanglement for communication requires classical channels, which are relativistically limited. The universe's structure prevents quantum mechanics from providing a loophole around light speed limits. The holographic principle and Bekenstein bound impose additional limits on information storage and transfer. The Bekenstein bound, derived by physicist Jacob Bekenstein, states that the maximum amount of information that can be contained in a given volume of space is proportional to the surface area of that volume, measured in Planck units. For a sphere, the bound is approximately 2 pi er, cc, where E is the total mass energy, r is the radius, c is reduced Planck's constant, and c is the speed of light. This bound implies that there's a maximum information density in any region of space. You cannot pack arbitrary amounts of information into a fixed volume. The universe itself limits information storage. For communication across intergalactic distances, this means that even perfect technology cannot transmit more than a finite amount of information using a finite amount of matter and energy. Consider a civilization wanting to transmit its entire knowledge base, all its science, art, history, and culture to another galaxy. The information content of this transmission is measured in bits. Even if transmitted as perfectly efficient quantum information, the amount of matter energy required to encode and transmit this information is limited by the Bekenstein bound. For sufficiently large knowledge bases, the mass energy required approaches or exceeds stellar masses. Furthermore, transmitting this information across millions of light-years requires that the signal maintain coherence and detectability. Quantum information is extremely fragile. It decorates when it interacts with the environment. A quantum state transmitted across intergalactic space would interact with the cosmic microwave background, stray particles in the intergalactic medium, and various radiation fields. These interactions would cause the quantum information to decohere long before reaching its destination. Classical information bits encoded in conventional electromagnetic signals is more robust but faces its own limits. The Shannon-Hartley theorem establishes the maximum rate at which information can be reliably transmitted through a communication channel with a given bandwidth and signal-to-noise ratio. For intergalactic communication, the signal-to-noise ratio is extraordinarily poor. The signal must compete with the cosmic microwave background, radiation from the transmitting galaxy, radiation from intervening matter, and noise in the receiver. The power required to transmit a detectable signal across intergalactic distances scales inversely with the square of the distance. For a signal to be detectable at Andromeda's distance of 2.5 million light-years, assuming reasonable receiver sensitivity, the transmitter would need to generate power levels comparable to the output of multiple stars. And this is just to transmit a simple carrier wave. Transmitting complex information requires even more power. The cosmic microwave background sets a noise floor for any electromagnetic communication. At microwave frequencies optimal for interstellar and intergalactic communication, because they penetrate dust and have low atmospheric absorption, the CMB contributes a background temperature of 2.7 Kelvin. Any receiver attempting to detect signals must distinguish them from this background. For signals from millions of light-years away, the received power is so low that quantum noise becomes significant, setting fundamental limits on detection sensitivity that no technology can overcome. Photon arrival statistics impose another quantum limit. Light, including radio waves, consists of discrete photons. A signal transmitted across intergalactic distances arrives as a stream of individual photons spread over time. At extreme distances, the photon arrival rate can become so low that distinguishing signal from noise requires integration times of years or decades. The receiving civilization would need to continuously monitor the sky for generations just to accumulate enough photons to decode a simple message. Even more problematic is the inverse square law combined with the vast collecting area required. A radio signal broadcast from Andromeda spreads out spherically as it travels. By the time it reaches the Milky Way, the signal is spread over a sphere with a surface area of roughly 1049 square meters. A receiver with even a massive antenna, say 1,000 square meters, captures only an infinitesimal fraction of the total signal power, about 10, -47 of the original. This dilution is unavoidable and makes communication across such distances extraordinarily difficult, even with classical signals, let alone fragile quantum information. The metabolic requirements for multi-million-year missions. Beyond the physics and engineering obstacles, there exists a biological barrier rooted in the fundamental thermodynamics of life. Living systems, including humans, are dissipative structures that require continuous energy input to maintain their organized state against the natural tendency toward entropy. For a multi-million-year intergalactic journey, the cumulative energy requirements to sustain even a small population become astronomical, revealing yet another dimension of impossibility. A single human being requires approximately 2,000 to 2,500 kilocalories per day to maintain basic metabolic function, about 8.4 to 10.5 megajoules. This doesn't include energy for activity, climate control, lighting, or any of the technological systems necessary for survival in space. Over a typical 80-year human lifespan, this amounts to roughly 25,000 megajoules of food energy per person. For a journey to Andromeda lasting 2.5 million years, even at light speed, a single human lineage would require approximately 781,000 megajoules just for basic metabolism, equivalent to about 6,500 kilograms of perfectly efficient food. But spacecraft don't carry human lineages, they carry populations. To maintain genetic diversity over thousands of generations, a minimum founding population of roughly 500 to 1,000 individuals is required. Using the conservative estimate of 500 people, and assuming each generation lasts 25 years, the journey would encompass 100,000 generations. If the population remains constant at 500, the total metabolic energy requirement would be roughly 3.9 times 1014 joules, about 93 megatons of TNT equivalent. This is just for human metabolism, not including any technological energy needs. In practice, closed ecological life support systems are never 100% efficient. Growing food requires energy for lighting, if using artificial light, temperature control, and maintaining atmospheric composition. Water recycling requires pumping, filtration, and purification. Air recycling requires removing carbon dioxide and replenishing oxygen, processes that consume energy. Waste decomposition and nutrient recycling require biological or chemical processes, all of which have energy costs. Studies of closed ecological systems on Earth, such as Biosphere 2, revealed that maintaining a balanced, sustainable ecology is extraordinarily difficult, even with Earth's gravity, atmosphere, and proximity to the Sunday. Biosphere 2, a 3.14-acre structure in Arizona, attempted to create a sealed ecosystem supporting 8 people for 2 years. Despite enormous effort and investment, the experiment encountered severe problems. Oxygen levels dropped dangerously low, requiring external intervention, carbon dioxide accumulated, species diversity crashed, and the system proved unable to sustain itself. This creates an impossible requirement. The spacecraft must either carry sufficient reserves to compensate for millions of years of losses, adding enormous mass, or it must achieve recycling efficiencies far beyond what thermodynamics permits, which is impossible. Some losses are unavoidable. Atoms escape during maintenance operations, materials sublimate in vacuum, equipment wears and sheds particles, and even careful containment cannot prevent all losses over such timescales. Food production presents additional challenges. Plants require specific wavelengths of light for photosynthesis, which must be provided artificially using energy from the spacecraft's power systems. The photosynthetic efficiency of plants is typically 3 to 6%, meaning that most of the energy input is wasted as heat that must be dissipated through radiators. Growing enough food for 500 people would require continuous power input of hundreds of kilowatts, sustained for millions of years. The energy source for all these operations is another fundamental problem. Solar panels are useless in intergalactic space, where the nearest star is millions of light years away. Nuclear fission reactors require uranium or plutonium fuel that decays over time. Uranium-235 has a half-life of 704 million years, meaning that after 5 million years, about 0.5% would have decayed. This seems manageable until you remember that the reactor must also overcome the energy losses from radiation damage to its components, degradation of control systems, and the accumulation of fission products that poison the reaction. Nuclear fusion reactors, if they could be built reliably, would require hydrogen isotopes as fuel, deuterium and tritium. Deuterium is stable and could be carried, but tritium has a half-life of only 12.3 years, so it would need to be bred from lithium during the journey. This adds complexity. The reactor must not only generate power, but also breed fuel, maintain containment systems, manage plasma instabilities, and operate continuously for millions of years without major maintenance that would require components unavailable in deep space. Antimatter, as discussed earlier, provides the highest energy density, but must be produced using more energy than is released in annihilation, making it an energy storage medium rather than a source. Even if a civilization could produce and store enough antimatter for a multi-million-year journey, containment systems would need to maintain perfect magnetic confinement for the entire duration. A single containment failure would result in catastrophic annihilation, destroying the spacecraft instantly. The biological entropy problem extends beyond physical resources to information. Living systems maintain their organization through information encoded in DNA and implemented through cellular machinery. But DNA mutates. Cosmic radiation, replication errors, and spontaneous chemical degradation cause mutations at a rate of roughly 10, -9 to 10, -8 per base pair per cell division. For humans, with about 3 billion base pairs, this means several mutations per individual per generation. Most mutations are neutral or slightly deleterious. Over thousands of generations, slightly harmful mutations accumulate a phenomenon called genetic load. In normal populations on Earth, natural selection removes the worst mutations, and genetic diversity provides raw material for adaptation. But a small, isolated population of 500 experiences genetic drift that can fix even slightly harmful mutations. After 100,000 generations, the accumulated genetic load could render the population inviable, suffering from reduced fertility, increased disease susceptibility, and developmental abnormalities. This is known as mutational meltdown in population genetics. Small populations in isolation accumulate mutations faster than selection can remove them, especially when the environment a spacecraft is artificial and controlled, reducing selective pressure. The only solution would be active genetic engineering, continuously monitoring the population's genome and correcting harmful mutations. This requires technology and resources that must function flawlessly for thousands of generations, and it assumes perfect knowledge of which genetic variants are harmful versus neutral or beneficial. Even maintaining the knowledge necessary to operate and repair the spacecraft's systems over thousands of generations presents a metabolic burden. Education requires time, energy, and resources. Each generation must be taught everything necessary to maintain the mission. Engineering, biology, physics, computer science, medicine, psychology, and countless technical skills. If knowledge is lost, a few generations fail to adequately train the next, the mission could fail catastrophically, as the crew loses the ability to maintain critical systems. The psychological and cultural stability required also has metabolic implications. Conflict, depression, and social dysfunction reduce productivity and can consume resources in conflict resolution, medical treatment, and potentially violent outcomes. Maintaining social cohesion over thousands of generations requires careful governance, conflict resolution mechanisms, psychological support services, and possibly enforcement systems, all of which represent energy and resource expenditures that add to the mission's metabolic burden. Childbirth and child-rearing represent substantial metabolic investments. A pregnant woman requires about 300 additional calories per day, roughly 10.5 megajoules over a 9-month pregnancy. Infants and children require care, food, and education for 15 to 20 years before becoming productive crew members. During this time, they consume resources without contributing to spacecraft maintenance. For a stable population, Enough children must be born to replace deaths, meaning a continuous fraction of the population is always non-productive dependence. The inevitability of catastrophic cascade failures. The final and perhaps most insidious barrier to intergalactic travel is the statistical certainty of cascade failures over multi-million-year timescales. Complex systems, particularly those far from equilibrium like spacecraft and living ecosystems, are vulnerable to cascade failures where one malfunction triggers others, leading to rapid, catastrophic collapse. Over the enormous timescales required for intergalactic journeys, such failures become not just possible but inevitable. Complex systems contain thousands or millions of components. A spacecraft suitable for an intergalactic journey might contain billions of individual parts when you count every transistor in every computer chip, every rivet in the structure, every seal in every valve, every wire in every cable bundle. Even if each component is extraordinarily reliable, say, an MTBF of 1 million years, the probability that all components survive 2.5 million years is vanishingly small. The mathematics is unforgiving. If a system contains n independent components, each with reliability r over time period t, the system reliability is Rn. If you have 1 million components, each with 99.9% reliability over a certain period, the overall system reliability is 0.999. 1 million is approximately equal to 0.0000453, less than 0.005%. The system will almost certainly fail. Redundancy helps but cannot solve the problem. If each critical system has a backup, and that backup has its own backup, you've significantly improved reliability. But over millions of years, even highly redundant systems fail, and redundancy has limits. Each redundant system adds mass, complexity, and consumes resources. You cannot add infinite backups. More problematic is that spacecraft systems are not independent, they're interconnected and interdependent. A failure in the power system affects life support, propulsion, computing, and communications. A failure in thermal control affects electronics, structure, and biological systems. A failure in computing affects automated systems, navigation, and monitoring. These dependencies create pathways for cascade failures, where one failure propagates through the system, triggering multiple subsequent failures in rapid succession. The Columbia Space Shuttle disaster in 2003 illustrated cascade failure. A piece of foam insulation detached during launch, striking the leading edge of the shuttle's wing and creating a small breach in the thermal protection system. This single, seemingly minor failure led to a cascade during re-entry. Superheated air entered the wing through the breach, melting internal structure, causing the wing to fail, leading to loss of aerodynamic stability and breakup of the entire vehicle. 7 astronauts died because a chain of dependencies connected a small foam strike to total system failure. On Earth, with ground support, engineers can often interrupt cascade failures. Monitoring systems detect anomalies, ground controllers analyze data and send instructions, astronauts implement emergency procedures, and if necessary, missions can be aborted. For an intergalactic spacecraft, there is no ground support, no abort option, and communication delays make real-time intervention impossible. The crew and automated systems must handle every failure autonomously. Automated systems themselves are vulnerable to failures and cascade effects. Software bugs, hardware glitches, and accumulating errors can cause automated systems to malfunction in unpredictable ways. The longer a system runs, the more likely it encounters an edge case, an unexpected combination of inputs or states that causes malfunction. Over millions of years, even extraordinarily rare edge cases become likely. The spacecraft's ecological system is particularly vulnerable to cascade failure. Biosphere 2 demonstrated how quickly ecological balance can collapse. In that experiment, oxygen levels fell partly because unexpected population booms of oxygen-consuming bacteria depleted oxygen faster than plants could replenish it. Carbon dioxide levels rose, affecting plant growth, creating a feedback loop. Similar cascade failures in a spacecraft biosphere could be catastrophic. An algal bloom in the water recycling system could produce toxins that poison the water supply. A fungal infection could spread through the food crops, destroying nutrition sources. A virus could sweep through the population, killing vulnerable individuals and disrupting operations. An invasive insect species could multiply unchecked, disrupting the planned ecology. Each of these scenarios could trigger cascades where the initial problem causes multiple secondary problems that amplify the crisis. Social and psychological cascade failures are equally dangerous. A charismatic but unstable leader could trigger a social crisis that destabilizes governance. A cult could emerge that rejects the mission's goals, leading to sabotage or violent conflict. Generational trauma, perhaps from an earlier crisis, could propagate through culture, creating psychological vulnerabilities that explode in later generations. These social dynamics are unpredictable over short timescales and essentially impossible to model over thousands of generations. The concept of normal accidents, developed by sociologist Charles Perrow, argues that in complex, tightly coupled systems, accidents are inevitable not from negligence or poor design, but from the inherent properties of such systems. Complex systems have many components with non-obvious interactions. Tightly coupled systems are those where processes happen quickly and changes propagate rapidly, leaving little time for intervention. Spacecraft are both complex and tightly coupled, making normal accidents not just possible but guaranteed over sufficient time. Historical examples of cascade failures in shorter missions are instructive. Apollo 13 experienced a cascade when an oxygen tank exploded. The explosion damaged other systems, vented oxygen into space, disabled fuel cells, and forced the crew to abandon the command module for the lunar module. The cascade was arrested only through extraordinary effort by ground controllers and crew, working together with communication delays of only a few seconds and support from Earth's resources. An intergalactic spacecraft crew would have none of these advantages. The accumulation of small, unrepaired damages over time creates vulnerability to cascade failures. A micrometeorite impact creates a tiny crack in a structural member. Years later, thermal cycling fatigues the metal near the crack, extending it. Decades later, a vibration event causes the crack to suddenly propagate, failing the structural member and causing a chain reaction through the connected structure. Each small damage seems insignificant alone, but their accumulation creates fragility. The ultimate cascade failure is extinction of the crew. If a disease, accident, or crisis kills enough people, the population may fall below the minimum viable population size. This triggers genetic and social cascades. Inbreeding increases, genetic load accumulates, loss of specialized knowledge occurs, and social cohesion breaks down. Once population drops below a critical threshold, recovery may be impossible, and the population enters a death spiral toward extinction, with the spacecraft becoming a tomb traveling forever through an intergalactic void. The statistical inevitability of cascade failures over multi-million-year timescales means that even if every other barrier could somehow be overcome, even if we had unlimited energy, perfect propulsion, and magic solutions to all the physics problems, the mission would still fail because complex systems cannot maintain functionality over such durations. The universe doesn't just lock us in our galaxy with distance and physics. It seals the lock with the relentless mathematics of entropy, failure, and cascade collapse.